other substitution. So the first one is rationalizing substitutions. That is, since some functions which are not rational can be changed into rational, so we know that we can rationalize something. If it wasn't rational, we make it rational. Like normal numbers like 1 plus root 2, maybe it's in the denominator, then they tell you to rationalize it. So you can change things and have a constant in the denominator. So the same approach that you're taking to functions. For example, if you have a function in this form, so you can deal with it by taking a substitution of letting this to be your u, this to be your u, and then you have something like that. Of course, the next thing will be to power with u. If we are to go on this, you bring n there and also on the left, so that you have un is equal to g over, is equal to gx. So you change things in that form and then solve your x, because the right hand side will be a function. So let's look at examples. Where, for example, A, evaluate A x over root of 1 minus x and then dx. Now if you look at this function, you cannot easily say, okay, let my u be 1 minus x, and then you differentiate, you get x. You cannot do that. Again, you can't use a long division to break this because of the root down. So the only way here is to do a substitution where you let your u to be the whole denominator, 1 minus x, and then immediately you square, just like we did there, and then have u squared is equal to 1 minus x. From there, you solve for x. So if you bring x to the left, to come as a positive, and then u to the right will go as a negative. So you have such a thing. But before you do so, you could differentiate also. So at this point, you can differentiate x with respect to u, and then we'll get negative 2u. So that if you solve for x, for dx, you get negative 2u du. So that when we come back to our integral, we'll come here with x being 1 minus u squared, and the root of 1 minus x being u. Remember, our first substitution was u is equal to root of 1 minus x. Then we had to square for it to be simplified. Then the dx, it has become that, negative 2u du. So everything now has changed. So what do we have? We now have everything in terms of u. So if we expand the numerator there, we'll get negative 2u plus 2u to the power 3. And we are dividing by u throughout, and then du, which gives us the integral of negative 2 plus 2u squared du. Then you can now integrate, where we get negative 2u plus 2 over 3 u to the power 3 So there's nothing. We just add a constant. Plus a c. So to present as your answer, you can't go with a c. What do? You present it in the same manner it came in terms of x. So you go back to our u. Our u is root of 1 minus x.
Isn't the u supposed to be 4 on 2 over 3 u to the power 3? Isn't it not supposed to be 4?
2 over where? You mean here?
Because when we were integrating, when
Do
we
you mean
were
this part?
integrating, we had negative 2u. No, I mean the final part, because you've maintained the cubed on the u instead of it becoming 4.
No, we haven't maintained. So look at here.
Oh, sorry. Okay, I've seen.
All right. So now we have negative 2 from here. The u is 1 minus x root plus 2 over 3 and then 1 minus x to the power 3 plus c. So we have such substitutions. This is called the rationalizing substitution. Okay, let's look at B. So B, you integrate the root of 1 plus the root of x over x dx. So in this case, so the most complicated one is the one that you make to be or u. So the most complicated in this case is the numerator. 1 plus root of x inside the root. Then from there now, you start looking for x. So you square, you also square on the left. So you have u squared is equal to 1 plus root x. Then from there, you take the one the other side so that we have u squared minus 1 is equal to root x. So again, we'll have to square. Also square. So that x is equal to u squared minus 1 squared. From there, we now have our x. So you can differentiate it. So what will be the x? So when you're looking for the x, you're trying to come and find a substitution there. You've already found for x. Now what about for dx? So we differentiate x with respect to u. So you get 2 u squared minus 1 multiplied by 2u du. So if we simplify it, it will be 4 u3 minus 4 u du. So that is the dx. So when we go back, we'll have the whole numerator to be u over the whole denominator x is u squared minus 1 squared. And then the x is 4 u to the power 3 minus 4u du. Or the best way to write it, since we are looking at the denominator, would be to bring it in an unsimplified manner. In unsimplified manner. In that form. So you bring it as 2, or should we say 4u? Let's say 4u, and then u squared minus 1 du. So I've done that deliberately so that this part can take away the power here, right? Since we have 2. And then we should have 4u by u. We'll get 4u squared over u squared minus 1 du. At this point, we bring in the long division because the powers are equal. So it becomes an improper fraction. So we bring in the long division where we say u squared minus 1 is outside, and then we have 4u squared. So u squared into 4u squared, we'll get 4, and then when we multiply back, we'll have 4u squared minus 4. Then we subtract, and we have positive 4. So our integral now has changed to 4 plus 4 over u squared minus 1 is the same as u minus 1 and u plus 1. Everything du. Then from here now, we'll have to get 4 over u minus 1, u plus 1, and break it into partial fractions where we have that and this, where we get a u plus 1 plus b u minus 1, and so this is equal to 4. So we know that we have a plus b is equal to 0, and also a minus b is equal to 4. So if we do the addition, we'll get 2a is equal to 4, so that a is 2. If we subtract it, we would have 2b is equal to negative 4, so that b is equal to negative 2. So what are we having? We are having the integral of 4 du plus 2 integral of 1 over u minus 1 du minus 2 integral of 1 over u plus 1 du. I hope you're able to follow here.
Yes.
Okay. Then the integral of 4 will be 4u plus 2 ln u minus 1 minus 2 ln u plus 1 plus c. The work now is getting back to our u. So we need to get back to u in everything. So we have 4u plus 2 ln u minus 1 plus 2 ln u plus 1 plus c, but u is 1 plus root x, root inside. Is it? Yes. So before we square this, it was 1 plus root x. Okay. So we can't leave our answer in terms of u. We must leave our answer always in terms of x. So we'll have 4 the square root of 1 plus root x plus 2 ln square root of 1 plus root x plus 2 ln what have I done? I've written the 4. So I was okay. 4 u is 1 plus root x plus 2 ln 1 plus root x minus 1 plus 2 ln 1 plus root x plus 1 plus a constant c. So that becomes our answer. So nice, right? It's not very complicated to follow when you have the once you have done a right substitution for u. And when you start substituting, what remains now is to make sure that you get to x. No matter how complicated the x is, you should extract it. Because you notice that here, x was inside the second root, but we had to extract it. And after extracting it, that's where now you differentiate with respect to u, so that you can have your dx. Okay, so we got the next question. That was C, where we have the integral of 1 over root x minus the cube root of x dx. Okay, so of course, the way this one has been given, the previous one, if you had to follow the example, it was just the properties of ln. Yes. And this one is supposed to be minus here. Supposed to be minus. So now if they are subtracting, then you can divide. But in an exam, there's no harm in leaving it here. Okay. Okay. Now, the next one here, we have the root of x and also the cube root of x. So what we have is x to the power half and also x to the power 1 over 3. So if you want to express u in this form, you need to find the common denominator for 2 and 3. And then subject it to be x. I mean to be or u with x to such a power. so that when you multiply each, they'll be able to divide and give you a constant power. So you let, so we know that for 2 and 3, the closest one is 6. So let u to be equal to x to the power 1 over 6. So that if we power it with a 6 and 6 there, then we have x is equal to u to the power 6. So that the dx is going to be 6u to the power 5 du. So if you come back to the substitution, what you have is, where there's root x, we know that root x is the same as x to the power half, right? So since our x is u to the power 6, when we half it, it will become u to the power 3. And also x to the power 1 over 3, since our x is u to the power 6, so when you bring 1 over 3 here, it will remain u to the power 2. So when you do our substitution, we'll have 1 over u to the power 3 minus u squared, and then the x is going to be 6u 5 du. So that this one becomes, so that it becomes the integral of 6u 5 over u3 minus u squared du. So how do we simplify it? We go through the same procedure. Since the power of the numerator is higher than of the denominator, you go to long division and break it there. So we'll have 6u5. So u to the power 3 in 6u5, it will give us 6u2, right? And then you multiply back, we'll get 6u5 minus 6u4. You subtract, you get 6u4, and then you divide again, it will give us plus 6u, so that we get 6u4 minus 6u3. And then you subtract, we'll get 6u3. Still dividing, we'll get 6, and then 6u3 minus 6u2. So that what we have altogether when we subtract, it will be 6u2. So this is going to be the integral of 6u squared plus 6u plus 6. So I can cut it here and say du, and then plus the integral of 6u squared over, we now write u3 minus u squared as u, and then u squared minus 1 du. So we are doing that, what did I do? Oh no, not minus u. So it has to be u squared, and then u minus 1, like that. Then now, we pick it and break it into partial fractions. So 6u squared over u squared u minus 1 is going to be a over u squared b over u, or you are used in this order, u and then u squared and then c over u minus 1, so that we have a u minus 1 plus b u minus 1 plus c u squared is equal to cu squared, I mean 6u squared. So if we expand, we'll get a u squared minus au plus bu minus b plus cu squared is equal to that, telling us that a plus c is 6 and b minus a is 0 and b itself is 0 from the constant part. So that's the only constant that we have. Yes. So what is this telling us? If b is 0, then of course a will be 0. So that c is 6. So our integral becomes the integral where 6 is common. So inside we just have u squared plus u plus 1, u squared plus u plus 1 du, and then plus that whole thing has been cancelled too. Oh, and actually there was even no need of going this far. I've just noticed that we could have just done this. You see that? So it wouldn't take us to the whole long division part. Okay. Then we integrate. So we have 6u3 over 3 plus 6u squared over 2 plus 6u plus 6 ln u minus 1 plus a constant c. But this is the same as 2u3 plus 3u squared plus 6u plus 6 ln u minus 1 plus c. So what is u? Where is our u? So u was from here, the u was x, the sixth root of x. So we'll have 2 x 1 over 6 power 3 plus 3 x 1 over 6 power 2 plus 6 x 1 over 6 plus 6 ln 6th root of x minus 1 plus c, which is 2 square root of x plus 3 cube root of x plus 6 6th root of x plus 6 ln 6th root of x minus 1 plus c. So we have this. Okay. It's okay?
Yes.
So we go to trigonometric substitution. And hyperbolic substitution. So all we need here is an extension of the trig substitutions. So this table is very important, where you have the expression. If you land yourself into such a thing, minus x squared, the trig substitution that you must expect is to let x to be a sine theta. Where we use sine theta, you could as well use cos theta. Why are we saying sine and cos are almost the same? Because when I use sine, the idea is if you let x to be a sine theta, then you will have a squared minus a sine theta squared. And this is going to be a squared minus a squared sine squared theta. So that a squared is common. So you have a squared and then 1 minus sine squared theta. Then from there, we now have the square root of a squared multiplied by the square root of 1 minus sine squared theta. The square root of a squared is just a, and then 1 minus sine squared theta is cos squared theta. So what we have now is a cos theta. So it can come out of the square root. So if we used a cos theta, then we would have a squared minus a squared cos squared theta. Okay? And this will still come out as a squared 1 minus cos squared theta. And then you have a, the square root of 1 minus cos squared theta, but this is just sine squared theta, where we just have sine theta. So it's coming, so all these trig substitutions are coming from the identities that leads to 1. So this is the first form. Then the second one from the table is if you have a squared plus x squared. Here you need to bring, so I'm still dealing with the trig substitutions. I haven't gone to hyperbolic. So here you bring x is equal to a tan theta. So that you say, okay, then I have a squared plus a squared tan squared theta. So that this becomes a squared, then 1 plus tan squared theta. And so what we have is a squared just remain with a, and then the square root of sec squared theta. Because we know that 1 plus tan squared theta is equal to sec squared theta. And so here you remain with a sec theta. So that if we swap the inside from this relationship, we also have that tan squared theta is equal to sec squared theta minus 1. So that if we had the swapped order here, we had x squared minus a squared, then we'll use x is equal to sec theta, a sec theta, so that we have a squared sec squared theta minus a squared, and then factor out the a squared, remain with sec squared theta minus 1, and then do that. Then we have a, the square root of sec squared theta minus 1 is just tan squared theta. So get a tan theta. The struggle here is we always want to come out of the square root, because inside the square root you cannot integrate. But once we are outside, we will quickly integrate. So this very relationship, if we go back to the identities for the hyperbolic sine and cos, you realize that we also have cos squared x minus hyperbolic sine of x giving us 1. That means that we can express this as 1 plus this. So when you go back to that, every time we have which expression? We have a squared plus x squared. You could also use this, because if we have a squared plus x squared, and then we let x to be a hyperbolic sine x, then we'll have a squared plus a squared hyperbolic sine squared x. This is going to be a squared 1 plus sine squared x. Hyperbolic sine. So that a comes out, and inside the root we now have cos squared x, and this will just give us cos x, hyperbolic cos x. Because of the identities, that's why we're driving all this. The same with tan x squared plus x squared x is equal to 1. This is now the one that takes the form of cos squared x. So if you have noticed, they have swapped. In trig, we have sine squared x plus cos squared x is equal to 1. We also have it was here 1 plus tan squared x is equal to sec squared x, meaning that meaning that sec squared x minus tan squared x is equal to 1. This is in trig. Hyperbolic trig, we have the opposite now. We have tan squared x plus this squared x is equal to 1. And then we have cos squared x minus squared x is equal to 1. So what we can do with cos and sine, we can also do with hyperbolic tan and the hyperbolic sec. What you can do with tan and sec, you can do with hyperbolic cos and hyperbolic sine. So it's very, very important. So that now you can start integrating the hyperbolic cos and the hyperbolic sine. So I think we'll do that in the next class. So next week we must move from Monday all the way up to Friday. Since we agreed that if your phone is off and the other one is on, we can have the class and have the recording. So I'm going to send the recording to the other student.
Okay.
Yeah. Okay, we end here. Have a good day.
Thank you.